Hello AP Chemistry and welcome to the last little bit of Chapter 17, talking about the common ion effect, and that eventually leads us into a Q versus KSP discussion. So, common ion effect, just like it says, right, it's the effect of having a common ion in the solution, right? So if we were talking about calcium fluoride, for example, okay, this says that the solubility of calcium fluoride decreases as a common ion is added to the solution, okay? So for example, right, so this is what we're talking about, right? Calcium fluoride, right? As common ion is added to the solution. So we can think about this from 2 points of view, right? So here in terms of this wording, is added, right? So it's saying like we already have ions and then the solubility decreases, right? So let's talk about that, right? Let's say that we have a container, right, wherein we have calcium fluoride solid and it is in equilibrium with its relative ions, right? If it's at equilibrium and we were to, I don't know, add some fluoride ions, what kind of analysis are we really doing? Right, this is a Le Chat analysis, right? Wherein if this system is at equilibrium and we were to increase the amount of fluoride ion, in which direction would the equilibrium shift to compensate for that? Right, it would go in this direction to compensate for the additional fluoride ions in solution. Now, when we say that's going to shift in this direction, though, specifically, this direction this time means forming CaF2 solid, right? Which means that, ding, 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 right, we're going to make more solid. We're going to form more precipitate, yes? And it's going to decrease the overall amount of fluoride ion in the solution, yes? Right? Which is why, right, the solubility of fluoride ion decreases as the concentration of, the solubility of calcium fluoride specifically decreases as the amount of common fluoride ion increases, yeah? So here we have fluoride courtesy of something else, right? And then my calcium fluoride decreases in solubility. All right, now let's talk about it from a more mathematical point of view, okay? Here it says we have some manganese hydroxide with this KSP value, where again the negative sign did not come with it. Calculate the molar solubility of manganese hydroxide in a solution that contains sodium hydroxide, right? So here, we're talking about the solubility of one thing in the presence of a common ion, right? So note that we're not talking about a specific chemical reaction here. We're just talking about a common ion, okay? So, what seems like a good place to start? Right, this is almost always a good place to start. So let's go ahead and get this down. So we know that this is our overall equation, right? Now, we can look at this from the point of view of a Rice table. There are other ways to look at it, and it just kind of depends, I guess, on what makes sense to you. This is just an easy, simple way to do it. So here, currently, there is none, right? We don't have any initially, but we do have 0.02 molar of that initially, right? Now, some of this will hopefully dissolve from here, right? Some of that will dissolve, which means that at equilibrium, I'm going to have x and 0.02 plus 2x. Yes? All right. Then we just set up my equation, right? I know that KSP equals my manganese 2 plus times my hydroxide ion squared, which is equal to 1.6 times 10 to the negative 13th, which is now also equal to x times 0.02 plus 2x squared, negative 13th, right? Now, if I go ahead and solve for x, right, x will give me the solubility of manganese ions, which gives me the solubility of my manganese hydroxide, yeah? All right, next up, Q versus KSP, all right, where again, Q is, right, an instantaneous picture of where a reaction is, and then I can compare my Q versus my K to decide what direction a reaction is going to move in order to reach equilibrium, right? So again, when we're talking about KSP, specifically, it is a salt dissociating into its respective ions, right? So if I was going to write the K for this, right, so again, let's go ahead and use this example. So here we have this, right? So that means my K is going to say Pb2 plus and Cl minus squared, right? My Q is also going to say, right, Pb2 plus and Cl minus squared, the only difference being, right, these don't have to be equilibrium concentrations. These can be the concentrations at any given point in time, and when I compare that to my K value, I can decide if the reaction is going to move forward or backwards. Now, again, if my Q is bigger than my KSP, what's that going to mean? What direction is my reaction going to go? Right, if my Q is too big, again, bearing in mind that all of these are product over reactant for the most part, right? That means I have too much product. So what am I going to do? Right, I'm going to consume product, and I'm going to form reactant, right? Now, if we look here, what does that mean? If I consume my products and I form reactant, right, that means precipitation, right? That means I'm going to precipitate, yes? Right? If my Q happens to be less than K, right, again, that means my K value is too small, right, that means I'm going to consume my reactant and form product, which in this case, right, if I form product, that means I'm going to dissolve, yeah? All right, so it's the exact same idea, just some of the terminology changes a little bit based on what we're talking about. But the essence is the same, right? Consume product, form reactant. We just have to be thoughtful about what product and reactant mean in the bounds of a KSP problem, okay? So, does a precipitate form, right? So we should be thinking KSP when we have some amount of NaF mixed with some amount of calcium nitrate. Now, is this a common ion problem? No, right? This is a reaction. These are two different things being mixed together. So we should start by, right, writing ourselves a reaction. So we have some aqueous this, we have some aqueous this, and it says that we're going to mix these together to form our products. What kind of reaction is this? Right, it's a double displacement. I meant to ask you to tell me that, and then I wrote it down, so then I ruined it. So how would I know if this was solid or aqueous? Right, based on our solubility rules, right? Group 1s and nitrates always soluble. Halide ions are soluble, right? Except for the fluorides. Now, so this would be our solid, which means that what do we need to know? Right, the KSP value of this. KSP value of this happens to be 3.9 times 10 to the negative 11. Okay. Now, we could go ahead and get a relevant equation, right? Let's just do, actually, no, let's not write it that way. So here now, we have a couple of things at play. Okay. So, things to think about. We have this reaction happening, right? And we form some calcium fluoride, and we know this KSP value. Now here, really important, if I want to talk about KSP, and I want to talk about if a precipitate forms, then here I think it's really helpful to go ahead and write the equation that corresponds to your KSP. Otherwise, it can get kind of confusing, right? I know that when I talk about a KSP process, I'm always talking about my solid dissociating into its respective ions. Yes, that's always what it means, right? And so my KSP then is always going to reflect that. Right? And I think that if you write this out, that will help to keep your brain organized. Because if we try to look at it from the point of view like, oh, calcium fluoride is my product, so then you want to write the calcium fluoride on this side with your ions in this side maybe, which is technically what's happening in the reaction vessel, right? But that doesn't correspond to what KSP means. And if our analysis is going to work with KSP, this is what we need to be looking at and thinking about, right? So, thinking about what I know, do I know my concentration of calcium ions? Yes, right? Between these pieces of information, I can get the amount of my calcium ions. Here, yes, I can get the amount of my fluoride ions. Do be mindful that we have to add these together, right? So we actually have a new molarity, right? So we'd have to take my moles of each, divide it by my new concentration, my new volume, to get the molarities of each of these. Once I get the molarities of each of these, I can plug that in, and that's going to give me my Q for this reaction, okay? Then I'll compare that Q to my KSP to see if my calcium fluoride is going to precipitate, meaning go in this direction, or if my calcium fluoride is going to dissolve and move in this direction. Yes? All right, so make sure you solve this, make sure you understand it, and make sure it makes sense. And if not, you need to come see me sooner than later. All right, thank you for listening. Be good, and I'll see you soon. Bye.